Now let's practice graphing transformed parent functions. So let's go ahead and try one of these graphs. Let's say we want to graph the function f of x is equal to a negative x plus 3 squared plus 5. If this is the case, we want to take a look at what our parent function is. Because it's squared or quadratic, we know it's going to be a parabola. But because we see the negative out here, it's a vertical reflection, meaning that it's actually going to be looking down like this. If we look at our inside, notice that we have a horizontal translation. So we're going to do x plus 3 is equal to 0 and see that x is equal to negative 3, which means we're going to move things 3 units to the left. We also see the plus 5, and that is a vertical translation, which means we're going to move everything up 5 units. So let's see if we can take a look at what our graph would be. So we said that we're going to move our vertex 3 units to the left, 1, 2, 3, and 5 units up. So that's going to be right around here. And then instead of going up, we're going to go down because of our negative reflection. And now we don't have any horizontal or vertical expansions. So what we can do is just go on ahead and use our normal table for our quadratic. For our quadratic, we would have 0, 0, 1, 1. Plug in 2, we get 4. Plug in 3, we get 9. So if that's the case, I'm going to do those same ideas. These numbers we're going to see me use every time when we talk about quadratic. So I'm going to go over 1 and down 1 because of our reflection. And then I'm going to go over 2 and down 4. 1, 2, 3, 4. And then over 3 and down 9. And I can now use what we call the axis of symmetry. Remember that parabolas, if you have the same thing on this side as you do on the other side. So using that information that I know, here's my vertex, that there's another point here, there's another point here, and there's another point here. So I'm just using the axis of symmetry, which is right here. And I'm going to go ahead and finish my graph. Now, it should be a lot smoother, but because of what I have to use in terms of making this video, it's not quite as smooth. So let's go on ahead and try another example with a different parent function. So let's say we want to graph g of x, where g of x is equal to the absolute value of x minus 5, close the absolute value minus 2. And again, we're going to do the same thing that we did last time and talk about the parent function. And we're going to see that our parent function is the absolute value. So we know it's going to look like a V. Because we don't have any reflections, it's going to be looking at an upward V. So we're okay. The minus 5 means we need to take a look at x minus 5 is equal to 0. X is equal to 5, which means we're going to go to the right 5 units. And then if we look back here, this is our vertical translation. Because it's minus 2, we're going to go down 2 units. So we're going to get our vertex that's normally at the origin and go down 2 and over 5, and that's where my vertex is. To graph absolute value, remember that we're going to just plug in numbers, and I'm plugging in the same numbers that we plugged in for the quadratic. Those are very useful. We can see that we're going to get that, and that kind of makes sense. So from my vertex, I'm going to go over 1, up 1, because that's what this says. Over 2 from the vertex, over 2, up 2. That's because that's what it says. From our vertex, over 3 and up 3. And we can see that this is part of my absolute value. Again, this also has an axis of symmetry. So I can see on the other side, or you can plug in values. And remember, when I plug in negative 1, the absolute value of that is positive 1. So I went to the negative side and still go up 1. Go to the negative 2 and then up 2. So from the vertex to the left 2 and up 2. From the vertex to the left 3 and up 3. And we're going to see that that's where our absolute value is going to go. And notice I did complete my graph and I made it fill in the entire grid. That's a good habit to get into, so it makes it easier for both you and me to see what you're graphing. Now let's look at graphing piecewise defined functions. If we look at this g of x, it actually has three parts that it's being defined. One of them is where g of x is equal to negative x plus 3. That's this top one. Another one is when g of x is equal to x minus 2 squared. That's the second one. And the third one is where g of x is equal to 1. That's this bottom one. So what we're going to do is graph each one of them as if they were by themselves. So I'm going to go ahead and graph this one right here. It's a line that has a y-intercept of 3 and a slope of negative 1. So I'm going to come up to 3, a slope of negative 1. You can see me graphing the dots, and then we would connect them. Now, the second part of that defined graph says it's only good for values where x is less than 1. So in other words, if I look at my number line and I find 1, I'm only going to have graph on the left side of that 1. So if I highlight where 1 is, that's right here. And that means that I need to get rid of all of this part of my graph because I only want the stuff that's on the left side. Notice that it says that it's not equal to 1, so I should have an open circle. So I'm going to write an open circle right here. When the x value is equal to 1, there's an open circle here. So now let's graph. So that's how we graph the first one. The second one says g of x is equal to x minus 2 squared. That's quadratic, and we know that it's been moved 2 units to the right. Remember what I'm doing here. I'm doing x minus 2 is equal to 0. X is equal to 2, so it tells me that I moved 2 units to the right. So from the origin, I go 2 units to the right, and then I'm going to graph my quadratic parent function, which is over 1, up 1, over 2, up 4, over 1, up 1, over 2, up 4. And we can see that this is my quadratic equation. But notice we have a part that says it's only good between 1 and 3, and it can equal to 1 and 3. So on my number line, where there's a 1, I'm going to have a closed circle. When there's a 3, I'm going to have a closed circle, and I'm going to have graph in between. So I'm going to go ahead and highlight that in purple so that we can see that. So here's the 1, and here's the 3. So what this says is that if you're not in between, then you need to get rid of it. So let me get rid of the outside parts of my graph. Remember it said that it was equal to, so where my red one is, I'm going to have solid circle. So last but not least, we need to graph this last one. So this one, remember, is a constant, so it's just going to be a horizontal line at y is equal to 1. There's my graph. But this one has a restriction that says x is only good as greater than 3. So when we go to 3, we're only going to graph what's on the right side, and we're going to have an open circle. So let's graph that. So again, I'm going to highlight my 3 in green, and then we get to keep everything that's on the right side, but we get to erase everything that is on the left side. And we said we're going to keep an open circle. So our graph is exactly what we see here. So I'm going to put everything in black so you can see what our graph looks like. Open circle here. Here's my parabola portion with closed circles. And then here's my constant. So it continues this way, and it continues that way. So let's talk about domain and range for this particular function. So remember the highlighted parts, the ones in yellow, purple, and green, are not part of my graph. Let me see if I can get rid of those. So let's think about the domain. Remember our domain are what all the values of x. I like to start over here on the left side and work my way towards the right. And notice that this guy is over here, way over here at negative infinity. So my domain is going to start at negative infinity. As I come towards the right, we can see we go all the way down until we get to 1, and then we have an issue But notice it is defined when x is equal to 1. I get this red dot right here. So 1 is still included. We come around, it's still defined everywhere, and is defined all the way this way, all the way till we get to negative infinity. So our domain for this one is actually from negative infinity to positive infinity. When we take a look at range, we're going to do the exact same thing. This time we're going to take a look at the y values, and I like to start from the bottom and look on my way up. So notice there's nothing down here. And first time we see our graph that hits my y value is going to be my x-axis. So we're going to say that it includes the 0, because this is a y value is equal to 0. It can be any number it wants to be between 0 and 1, so that's good. But when we get to the 1, notice it can be 1, but it cannot be a little bit above the 1. So we're going to say it's going to equal to 1, and then it's going to start again at 2, but not equal to 2, so that's the reason why we have an open parentheses. And we're going to have that going on forever and ever and ever. So that goes to infinity. So there's your quick review of transformed parent functions, piecewise functions, and a little bit about domain.